Okay, so what I want to go over now is average atomic mass. So I want to give you guys a little bit of background for this, and then we're going to go over calculations. So when we look at a periodic table, what you should notice is most of the elements on the periodic table have a decimal and several numbers following the decimal when we look at their masses on the periodic table. This is because these are actually the average atomic masses that are listed on the periodic table, and we'll go over how these are calculated. Now, most elements that we have in the world around us have many different isotopes. Some of those are going to be unstable, they'll be radioactive, and some of them will be stable. So when we call something an isotope, we're not implying that they're dangerous. We're just saying that they have a specific number of neutrons. So when we're talking about large amounts of an element, to describe the mass of it, we talk about the average atomic mass of that particular element. And this takes into account the naturally occurring isotopes when we do the calculation. Because atoms are so small, we do not use grams to describe the average atomic mass. We instead use a special unit which has been created for atoms, which are called AMUs, or atomic mass units. AMUs are atomic mass units. One atomic mass unit is 1/12 of the mass of a carbon-12 atom. So one AMU is going to be one proton or one neutron, the mass of one proton or one neutron. So one AMU is equal to one proton or one neutron. Now, to calculate the average atomic mass, I want to show you the formula. It's going to be the weighted average of the masses of all the isotopes. These are, like I said, the average atomic mass is what we see listed on the periodic table. And when you get your answer, you can round it to 2 decimal places. So in this formula here, this is just for simplicity's sake, but there can be many, many, many different isotopes. So this could go on, and it will depend on how many isotopes a particular element has as to how long that calculation will be. Okay, so I want to go over some problems that are on your worksheet that's on Google Classroom, and let me pull that up. So you're going to be working on the Abundance of Isotopes worksheet, and again at the top they have the summary of the calculation. And you notice here at the top they do not divide by 100. If you convert each of your percentages to decimals, you do not have to divide by 100, but just be very careful if you do your calculation this way. So I want to show you number 2, and number 1 is actually just a thought problem. So if you look at argon on the periodic table, I want you to notice which isotope the average atomic mass is closest to, and that would be the one that is most abundant in nature. So you do not have to do a calculation for number 1. For number 2, some students can be thrown off by the information, so I want to show you which part of it you will use in your calculations. So I've copied number 2 on the next page, and if you look at it, they give you both the mass number and the mass for the different isotopes. So when we're doing this, what we're going to be using is the percent abundance, and we're going to use the mass that's listed in AMUs, the percent abundance, and the mass in AMUs. So the mass number is just some extra information. You do not have to use that. You are going to be using the information I've highlighted. And this will be true of the other problems on this worksheet. So for copper, the average atomic mass this is going to be, let me move this, is going to be 69.17% times 62.9296 AMUs plus 30.83% times 64.9278 AMUs. And this will be over 100. Now, when you're doing these, it's really important that you kind of estimate in your mind which mass you think your answer will be closer to. That should always be the one with the higher percentage. The reason why is that it's very common for students sometimes to make calculation errors when they enter their information into the calculator and then to not realize that they're getting the wrong answer when they're done. If you make an estimate, you're more likely to catch those mistakes and not make as many errors on your test. So let's do this. And your answer should be 63, and I'm going to round it to 2 places past the decimal. It'll be 63.55 AMUs. And if I look up above, this is about 0.6 away from the first isotope. It's about 1.5 away from the second one. The first one is most abundant, so that answer makes sense. Okay, so I want to go over one more problem that's on the sheet. So if we look at number 7 on the sheet, this is probably the most difficult problem. So I want this one together, and then hopefully after you see number 7, then you will have no trouble working through the rest of the problems on this worksheet. So I copied number 7 on the next page, and what we have here is a situation where we're going to be working backwards. So we have antimony, and it gives us the masses of the 2 isotopes of antimony, and it wants us to find out the average, the percent abundance of each of those isotopes. So we're going to have to be working backwards using our periodic table. Now, we know if we look at the periodic table, what we can see is we could find antimony's average atomic mass. And on periodic table, the average atomic mass of antimony is 121.8. So we have 121.8 AMUs, and we're going to equal that to the mass of each of the isotopes. First one is 120.904 AMUs. And we're going to say that the percent abundance of this one is X. And then we're going to add that to 122.904 AMUs. And since these have to add up to 100, we're going to say the second one is 100 minus X. Now, we're going to divide this by 100, and then what we want to do is get the like terms together. So we want to get X by itself. So we're going to multiply each side by 100 first. So it's going to give us 121.80 AMUs is equal to 120.904 AMUs times X plus 122. I'm going to multiply that by 100 AMUs minus 122.904 AMUs X. Okay, so now I'm going to have to bring over that 122.904 to the other side. So I'm going to subtract this from both sides. Okay, when I do this, I'm going to get negative 110.4 AMUs. And then I'm going to combine these like terms on the other side. And I'm going to get 120.904 minus 122.904. That's going to give me 2 AMUs. And then I'm going to have to divide each side by 2. And so that's going to give me 55.2% is equal to X. So the first one is going to be 55.2%. And the second one is going to be 100 minus that, which is going to give us 44.8%. So it gives me the 2% abundances. Okay, so hopefully you follow that. If you have questions about that, please let me know. But try all the problems on this sheet. And like I said, email me if you have any questions.